So welcome everyone to our 9th birthday. For this happy celebration, we have a indeed beautiful summer day. Honestly, my favorite weather in the German summer. And we have almost 20 people with us on board. And we have 2 great talks. And the schedule for the day will be, we first have a talk by Billy, and then we have a Q&A, and then we have announcements, and then we have an open mic. And that's also the chance to tell us about, you're looking for a job, or looking for colleagues, or looking for contributions to open source projects and so on. And then we will have a short break, and then we will have a talk by Adrian, and then we'll have more Q&A, and then we'll move to Slack to do more networking. And everything is recorded. So the talks are recorded, the breaks and the Q&A are not recorded. Everything is uploaded to our YouTube channel. The link is on Meetup. And we're also tweeting everything. We are GDG Berlin Golang. What else is interesting to mention? The breakdown of attendees is always interesting. So let's look. We've been asking you all some questions. And are you using Go for fun or work? So exactly half are using for both. 35% are using only for work, 15% only for fun. How long have you been using Go at work? So it's a tie between 5 to 7 years and first year. Then we have 3 to 4 years. And then we have 1 to 2 years. And few people are more than 8 years using Go at work. How long have you been using Go for fun? So it's a tie between first year, 3 to 4 years, 5 to 7 years, and almost tie between 1 to 2 years and 8+ years. That's a cool mix of everybody on board, and that's probably the best crowd to have, because the speakers are going to get the coolest questions. Are you based in Berlin? 60% yes, 40% no. Nobody's in the process of relocating here. And 75% of the people are using Go 1.14 at work. Few are using 1.13, and few are using 1.12. And the festive question to celebrate our 9th birthday. So the earliest member we have attended the Go Meetup for the first time back in 2014. But exactly half started coming to this meetup only this year, probably because it went online, given that we have quite a few people from out of Berlin. So good things come from moving online. And then we have a mix of people coming throughout the different years, but second place is definitely 2015. So we have 5-year members, and that's really cool. Will be interesting to see the correlation between how long you've been using Go and how long have you been attending these meetups, but that's slightly too sophisticated for right now. So we'll crunch those sometime in the future. And without further ado, I would like to hand over the stage to our first speaker, Billy Rennekamp, who will give us a quick history of digital scarcity and forgivable money and introduction to the Cosmos SDK, which is a Go framework for building distributed deterministic state machines. Billy, please share your screen and have a great talk. So the way that the Q&A is going to work is that everybody will be no longer able to unmute themselves, but you are welcome to ask questions in the chat. And once the talk is over, Billy will be going over them and answering them. Please welcome Billy.
Thank you very much. Thank you very much. This is a shortened version of another talk that I've given in the past. I'll do my best to stay on a 30-minute schedule. Let's kick it off to not waste any time. So my name is Billy. I'm from Louisville, Kentucky. Been living in Berlin almost 10 years now. I'm a grants manager on the board of management on a Swiss foundation called the Interchain Foundation that's dedicated to open source software. Previously, I was a freelancer, but please call me a mercenary instead. I think it's a lot cooler. doing Ben Studio, which was a group of friends of mine and I doing dev and design work. Built a project called Clovers Network, which is a scarce digital game and artwork. Worked with projects Gnosis and Aragon Black here in Berlin. Favorite topics otherwise are JavaScript and Vue. I know I shouldn't be saying that here. Golang and the SDK is the topic on hand today. Been working with Solidity and Ethereum, as well as something called curation markets, and I'm a big fan of hackathons. The images on the left, of course, are to represent my lovely hometown, Louisville, Kentucky, the birthplace of bourbon whiskey, the fastest horse races in the world, and of course, the birthplace of bluegrass music. So to begin, I want to talk about digital scarcity as a primitive. And primitives inside of programming languages, you know, we're all familiar with. We have the lovely Boolean, things like string, you know, unsigned integers. But there's a new primitive which becomes possible when you have a very specific architecture. And that primitive is digital scarcity. You could also think of this as money, but when you typically work with money in software, you use numbers, integers, floats to represent money, but it's not money itself. You know, typically it's like a representation of money that gets redeemed by a merchant service like Stripe or some other API that interacts with a bank or something. The other thing I want to talk about briefly is just games as sort of worlds, immersive worlds that have their own economies. Worlds are economies, and that's what really makes a world real, I think, is when you start having persistent value. And so the idea of being able to have, you know, real value built directly into your programming language enables you to have a much more sort of persistent idea of a world, and that becomes really exciting, I think, in games. State machines is a term that was mentioned earlier, and it's being a little bit abused here, but the general concept is that you know, you have a state for a machine. Sometimes it's a way to represent a flow, but there's different actions which can change that state. In this situation, you have a light bulb. The state can be on or off. The action is flip switch. Depending on the current state, the action will do different things to change the state. We used the term deterministic state machine a second ago to sort of denote that if you were to flip those same sequence of flips, you're supposed to do it in the wintertime as if you were to do it in the summertime, you should still end up with the same result. You know, it doesn't matter what the other outside conditions are. You know, if it's deterministic, no matter how many times you replay those, you should get the same result. Cryptographic hashes are another sort of feature of this architecture that I'm dancing around right now while I'm describing. You're probably familiar with them mostly. They show up a lot in Git. You know, this is the sort of hash that you see in the current code base and the tree of previous ones. It allows you to have, you know, certifiable state, which is really exciting. Allows you to have really sane dependency reliability. You know, if you know exactly what state of all of your dependencies are, you know, you can kind of get a good idea of what's going in. I won't go too deep into that, but I guess I will. Hashing in general, though, is where you take an input. For instance, in this, it's a string, a few sandwiches short of a picnic. You can hash it, you get an output. Of course, if you change the smallest piece of the input, the output is completely different. This is a bit like, you know, it's a terrible metaphor now, I'm looking at it like a meat grinder. You've got Porky the Pig here. If you change this one little pixel from orange to red, you know, it's a completely different sausage that comes out. I'm quickly gonna go over, I know this isn't super Go related, but this has to do with something I'm getting to, I promise. Asymmetric cryptography. This is also known as public key cryptography. And generally there's two really exciting things you can do with this. But the way you begin it is by taking a really big random number. You run it through this key generation function and it results in a public key and a private key. Public key is something that you might publish on your profile. It's like a user ID, something that's very public. You want everybody to know you're associated with. And your private key is, you know, private. You keep it all alone. One of the things you can do is send secret messages with it. So imagine I'm Bob and I want to send a message to Alice. Of course, this is Bob Ross and Alice Cooper in this example. I'm Bob and I want my message to be really secret when I send it through the mail. Because Alice published his public key, like everybody does, I can get a hold of it and I can use that public key to scramble my message. I can encrypt it. And then when I send that encrypted message, nobody can see it. Only Alice's private key is able to decrypt it, so he's able to see, oh, it's a message from Bob and it says, hello, Alice. Great. Alice, you know, wants to show that he appreciates me as a fan, so he makes an autograph for me. This is sort of the other cool thing you can do with public key, private keys. He wants to, send me this autograph, but none of my friends are going to believe me that Alice Cooper signed, this message towards me. So the way that I can make sure that it's proven is that Alice will take the plain text, hello Bob, and he will sign it with his private key. He's the only one who has this. And that creates two things. It creates this sort of similar hash, but that paired with the original message in plain text, because he's not trying to hide the fact that he said hello Bob. He wants the world to know it. I want the world to know it. You take both of those things, anybody else can verify it was really signed by Alice's private key by using Alice's public key. So that way you can sort of confirm, yes, true, this message is authentic. It's a verifiable signature that came from Alice Cooper. Wow, how amazing. So public key cryptography is really a great way to handle sovereign identities, which is a feature that I think should be used a lot more across any stack of any language when you see especially internet applications. Instead of storing a bunch of users' passwords in a single database where if they get cracked open, all of them get exposed, even if they're salted or whatever, why not allow the users to keep their private keys themselves and then just store the public keys of all of these users on your database? When they want to log in, it becomes a little bit like a universal OAuth where they get to sign something locally that says, yes, right now at the time so-and-so, I want to access my information on Facebook. They send that signed message to Facebook. Facebook uses that public key to verify, oh, it really was that user who used that private key. I'll give them, a session and let them access their information for this, time period. That way, if Facebook is compromised, they don't leak every single person's private key, which is essentially the situation now. So if you take all of those things together, deterministic state machines, sovereign identity, you're able to have the necessary elements for digital scarcity. One last piece of it that's good to keep in mind is that when you're running an application that has real digital scarcity, real money built into the software, that's quite a responsibility for that app designer, the person with that architecture. So you probably want to sort of share the load of securing that value. And if you haven't figured out at this point, when I talk about deterministic distributed state machines, I'm talking about blockchains. And I have to apologize because you're probably familiar with this. When you think about blockchains, ICO hypes, Ethereum, Bitcoin, runaway prices, scams, and all these sorts of things. This is actually a screenshot from a website that the Security Exchange Commission in America made as a joke or as a tool to sort of inform people about the scams that are out there with most blockchains. But the reason that we're in that situation is because it's a piece of sort of fundamental core infrastructure which was funded in a completely new way. It was funded by the general public. And if you look at the internet, you have this massive timeline that was mostly funded by government grants and things like that to fund what is really similar infrastructure, but it's, it should be brain dead boring. Nobody really even knew that this stuff was happening until the 90s, but there's this massive timeline that took place. I mean, we're probably around 1981 if you were to make a comparison between blockchain and the internet. However, in 1981, you didn't have everybody and their uncle telling you to buy this token or something like that. It was just the boring internet. So forgive blockchain for being in the situation. It was funded in a completely new way, but the results sometimes are unsavory. We're currently in the third generation of blockchains. I just skipped over some slides because I didn't want to give too much of a background on that, but the first generation is Bitcoin, you can see on this left. Second generation is Ethereum. And the third generation is this idea of an internet of blockchains. And it really mimics the way that the internet today works. And it's the idea that there should be a bunch of different blockchains that each have their own features, built out of their own programming languages with their own stack for their own purposes, and that are connected through a permissionless communication protocol similar to TCP/IP. Because, I mean, the internet is not a single computer. Up to today, we're kind of been thinking about blockchains as a single computer that we should all be on, the world computer or something. But that's not how the internet works. And the internet's also not a single stack. Each single application or use should have its own features for its own purposes. Maybe Go is part of it, maybe Go is not. It has reasons that you would or would not. And for that reason, we kind of think this internet of blockchains or this internet interchain should not be a single network, but a series of networks connected. And that would result in something like probably a hub and spoke architecture, similar to the way the internet works. It's not that every single computer is connected directly to every other computer. They route through hubs. And so The project that I'm a part of is a hub, and they also build a Golang software development kit for making blockchains as applications. We like to think of it as a Ruby on Rails for blockchains. It uses some nice features like object capability, least authority. It's modular, so you can sort of import features the way you would have done with something like Ruby on Rails. It's extendable, obviously it's Golang, and it uses something called proof of stake for distributing the actual application itself. Proof of stake is called Tendermint, and it's actually an extension of Byzantine fault-tolerant consensus and networking protocol, which has been around since the 70s. It's just been modified to handle a lot more. So if you've ever needed to keep a distributed system in sync, you might have used Raft or PBFT. This is just part of that extended family, except for allowing a lot more participants who are actually strangers. You know, typically when you have PBFT, you've got like, you're running all of the nodes yourself. But if you were to say invite in a stranger to run one of the nodes that operated your network, you could do so safely with Tendermint. It has a 66% failure. So if you have, you know, a very large portion of the network who's trying to take you down for some reason because they're haters, I don't know what reason, you have a massive amount of fault tolerance. IBC is this communication protocol I mentioned earlier. It's really the equivalent of TCP/IP, but for deterministic state machines. It essentially allows you to send packets between these networks that contain evidence of the origin that can be verified on both sides. And the result is this sort of third generation architecture of blockchains, which is not completely live, but many pieces of it are now live. And the final sort of piece of IBC is something that you'll see come on the next few months, which we're pretty excited about. But it really results in the idea that you shouldn't be building blockchains, you should be building applications. You know, you should be thinking about these as apps that do a thing, not as like a get rich quick scheme, not as a Ponzi scheme, not as a pyramid scheme. You know, think about what is possible when you actually are building applications. And one of those features of the application is that scarcity is a primitive. I think one of the most exciting versions of that is gaming. So I'm going to briefly go over a very simple game that I designed that comes with a tutorial. Usually I would give an actual walkthrough of the tutorial and we could build this stuff together, but in 30 minutes, it's really not practical. So I'll go through a bit of the features of the game and talk a bit about the architecture of the SDK and how it's sort of been designed to make building new apps in Golang easy. And at the end, there's a link to that tutorial if you want to follow up with it another time. So this is a simple scavenger hunt. Basically, anyone can post a question with an encrypted answer. And each of those questions come with some digitally scarce bounty with basically a coin or a token that if you answer it correctly, you know, you receive that bounty. It's a bit like Rumpelstiltskin, which is why that creepy little guy is at the bottom of the screen. Something to consider with blockchains in general is the way that the state updates take place. So I'm a user and I want to change the state of this publicly run application. We use those sort of like the Alice Cooper signature method to make those updates. So similar to like the login with Facebook idea. You know, I take a message that says, I, Billy Rennekamp with, you know, public key ID, user ID number, whatever, would like to log in for the next 30 minutes. And then I sign it with my private key. In a state machine, I can do something similar, which is like, I, Billy Rennekamp, would like to post a challenge and I want this challenge to be recorded in this state machine, this application. I will sign that message with my private key, and then I submit that message to what are called the validators. The validators accept all of the incoming messages. They put them into blocks. Those blocks get processed in the state machine, and that's actually why they're called blockchains, is because all of the messages get grouped, and then they get processed in batches. When this happens, it means that there's sort of this middle phase where they're still getting grouped into this block. And in order for these networks to be operated by, you know, a public group of validators, you know, anybody could technically be operating the state machine collectively. There's this moment where they're accepting them, that everyone can kind of see the contents of those messages, even though they haven't been included in the next state update. So it's almost like I send the intention to switch the light, and somebody else sends the intention to switch the light off again. And until those those intentions have all been like ratified, you know, notarized, rubber stamped into this block and then processed, they're like, they're in the mempool, is what it's called. So anybody can see them. That's like a 5-second period, which is very long in computers. And so there's this potential in our situation. If I'm like trying to answer this riddle and I say, oh, I know the answer to that. Why don't I write it down on my thing? Then I'll be the one who gets this bounty. I sign it and I send it. There's gonna be 5 seconds where everybody can see my answer, and they'll say, oh, well, why don't I just also say the same answer, and I'll sign it and submit it. And depending on, maybe I can convince the current validator who's in charge of rubber stamping that mine came in a second before them. You know, there's 5 seconds, and I don't know what kind of negotiation, maybe you can pull off the chain, you know. We don't really want to think about the unsavory things that you could do, but you could potentially convince somebody to include your answer in front of mine in that state update, and then it would look like you knew it before me. So this is called front running. A similar capacity happens all the time in high frequency trading, in the stock market. You know, you put in a buy or a sell, somebody else puts one right in front of you, and you end up buying it from them instead. And so there's a really clever solution to preventing front running called commit reveal. And it uses this hashing tool that we talked about earlier. So it's 2 parts, commit and reveal. Commit is where you take your answer and your name, you combine it kind of like a tuple, and then you hash that. And similar to the sausage analogy earlier, when you hash that, it's going to result in a scrambled string. So then you sign that scrambled string and send it to the network. And the only thing that's recorded is that scrambled string. Nobody knows exactly what that's about until you send a follow-up transaction that says, haha, it was I who had the answer, and this is my name. And so if anybody else were to submit that answer and their name at that point, it would be submitted as a different transaction that results in a different hash. So the actual application itself is hashing this answer and name, and it only accepts it if a previous commit was found. So that breaks up this single transaction into 2 separate transactions that can't be front run anymore using cryptography, which is super cool. Just real quickly, I'll go over it because I'm sure that's going over a couple people's head. You want to prevent somebody from submitting the answer before you. So you basically submit proof that you know the answer. You know, I claim to know the answer by submitting this hash of the answer plus my name. And then later on, I can follow it up with proof that it was me who submitted that answer, and the app itself can verify that, yes, it was you, and yes, that answer is correct, so here's your bounty. And what's kind of cool about this is that it's a very simple mechanism, right? It's a very small piece of what could be a very, very large and interesting and complicated game. But you could imagine it fitting into games already today, augmented by other areas of software. So like Zelda is screenshotted right here. Zelda, you go around and you like find treasures, you beat bosses, and at the end of these, you might receive things. So you can imagine packing like a video game that includes some of these answers, let's say, to riddles, which were stored on a blockchain somewhere. And only once you've beaten the boss, does the boss provide you with that like secret answer that can be commit, reveal, submitted to an independent blockchain, and the actual real money can be distributed to the user. So you don't have to build in, you know, a graphics processor into a distributed state machine. That would be like way too much processing that you would want inside of what should be a pretty simple application. But you could augment an already built and running application with a real economy of real money that's inside of a state machine as real digital scarce value. Oh my God, that was way faster than I thought I would be able to do it. This is the link to the tutorial. Maybe I can talk a bit about the SDK itself. So I don't think I stored slides for this here. We can go back to that. Nope. So the SDK itself consists of these different modules, right? There's one just for securing it, which is the PBFT distributed consensus, and that's where you have these people deciding what's going to be included in the state machine. And as soon as it's included, it goes to a handler, and a handler basically says, okay, this message type is related to this module. Say the module is the scavenger module, and it hands off any of those messages to a keeper. The keeper is basically a simple key value store, which will process that message and update the result. So it's pretty simple, but there's a similar mechanism for reading data called the querier. The querier has a route, and depending on what the route is, it'll direct you to different keepers. When you design a module, you can import keepers from other modules. So this is the object capability, least authority, so that you never have sort of leakage between different modules that have different abilities. So the bank module is one that handles tokens. There's also one called the governance module. This is where you can sort of turn your application into a co-op, or almost like a business, where you can make collective decisions based on token votes. So your tokens can become something like, the right to make a vote, make a collective decision. These are sort of getting a little bit at some of the capabilities that you start seeing, or some of the use cases that often come into blockchains, when you have a group who has maybe different reasons to do different things, but they have one collective identity, and they might want to manage digital scarce assets in some way. That's sort of the business version of it. It's called a DAO sometimes, which is a decentralized autonomous organization. Feel free to look up a very, very long and obscene lexicon of blockchain terminology. I once heard that you should keep an eye on any space that's coming up with new words all the time. That means something's happening, and blockchain is definitely no exception to that. I like to try to focus generally, though, on what's possible at a technological level. I would warn anybody who's getting into the space that it's very easy to get overwhelmed on very lofty ideological levels. Many people are involved in this space for many different things, but I felt so empowered, and I think I first built my first Ruby on Rails app that I could actually build an application that did a thing. And I have a very similar experience with the Cosmos SDK as a framework for building deterministic state machines that have digital scarcity as a primitive. So I'll stop there, and I'll end again on my name. Where was that? I don't have any of my contact there, but so then I'll end on the last one. And that was a lot. I'm sure that there was many things that didn't come off right. Maybe I can end 5 minutes early and have 5 minutes more for questions or something like that.
First of all, thank you very much. I'm gonna stop the recording for the questions.